So welcome to Chapter 3 of Intro to Programming with C. Let's talk about structured program development. Basic problem-solving techniques, developing algorithms through the process of top-down, stepwise refinement, which is also known as waterfall. Use of if statements, if-else statements, while iterations. We talked about that in Chapter 2 and Chapter 1. We're also going to talk about the user-controlled iterations and sentinel-controlled iterations. We're going to learn about structured programming, and we're going to learn how to decrement, increment, and assign operators. Let's jump right in, shall we? So, before writing a program to solve a particular problem, we must have a thorough understanding of the problem. Now, that's not necessarily true. We should know majority of the requirements that are required, majority of the things which are required. You're not going to be able to solve all the requirements, but if you know what the majority of the problems are, or majority of the requirements to solve the problem are, it's easier to solve the problem in the code. As you know, a computer program is a set of instructions that we tell a computer to execute. A procedure for solving a problem in terms of the actions to be executed and the order in which these actions are to be executed is called an algorithm. Okay, so a procedure for solving a problem in terms of the actions to be executed and the order, actions in order, is called an algorithm. Correctly specifying the order in which the actions are to be executed is extremely important. And in some languages, as you'll find, like JavaScript, you inherently have to define what comes before what. Just because you write one line before the other doesn't necessarily mean that both those lines will wait for each other to run before they operate. So, consider the rise and shine algorithm, followed by one junior executive for getting out of bed and going to work. So here we go with the rise and shine. It basically talks about what you do in the morning before you get to work. Get out of bed, take off your pajamas, take a shower, get dressed, eat breakfast, and carpool to work. Now, of course, there's probably more steps in there, but this is kind of like the high level of what happens. If we decided that we wanted to make a change to this specific procedure or this specific event, the events that occur in this algorithm, you get a very different result. So if it was get out of bed, take a shower, take off pajamas, obviously that probably wouldn't be a good idea, taking a shower with your pajamas on, as that would sound. So getting this right is very important. And we just talked about this, suppose that the steps were different. Get out of bed, take off pajamas, get dressed, take a shower, eat breakfast, carpool to work. The executive will show up soaking wet in their clothes because they took a shower after they got dressed. So I know this might sound a bit asinine, even intuitive, but computers are not intuitive. We have to be very specific about what we want the computer to do and how we want it to do it. Pseudocode is an artificial and informal language that helps you develop algorithms. It is also a very interesting way to write languages or write coding languages or computer programming statements using regular English. Pseudocode is similar to everyday English. It is everyday English for the most part. And you cannot execute pseudocode programs, or more specifically, you cannot execute pseudocode on computers. They're basically for us to understand what we're doing. So rather they help us think out a problem or think out a program before we attempt to write it. Whether that's C#, C++, Java, it makes life a lot easier. And it consists purely of characters that we understand as humans. A carefully prepared pseudocode program may be converted easily. Just understand that pseudocode makes it easier to write what you need to write. It's an outline. It's the same as writing an outline for your essay for English, reports for geography, or whatever class you're taking. Writing that outline can really help you in understanding the direction you need to go while you're coding, so you don't feel like you're kind of lost or get writer's block. Pseudocode consists only of action and decision statements. So those that are executed when the program has been converted from pseudocode to C and is run in C. Definitions are not executable statements. They're simply messages to the compiler. Just understand that pseudocode can't be run by Visual Studio or anything like that. It's basically for our SA, for our situational awareness. So here's an example. For example, the definition int I, what does that mean? So basically what they're doing is they're initializing a variable, the variable I, as a data type integer. It tells the compiler the type of variable I and constructs the compiler's reserved space in memory for the variable. But this definition does not cause any action, such as input, output, or a calculation or a comparison to occur when the program is executed. Some programmers choose to list each variable and briefly mention the purpose of each at the beginning of a pseudocode program. You don't have to, but it's a widely accepted way of writing an outline to your program. So, what are control structures? Well, normally statements in a program are executed one after the other in the order in which they are written. This is called sequential execution, or in the real world we call this waterfall, meaning that the line after the line being executed cannot execute until the line before it executes without error. Various C statements we'll soon discuss enable you to specify that the next statement to be executed may be other than the next one in the sequence. This is called transfer of control, meaning that at some point in time I might have called a module or something that's not necessarily directly after the code the statement that I wrote. In that case, and there's reasons for that we'll get into later. During the 60s, it became clear that the indiscriminate use of transfer of control was the root of a great deal of difficulty experienced by software development groups. Not having a clear distinction of what happens next kind of led to the object-oriented programming techniques that we employ today. And this is going to go a little deeper into it, but the finger of the blame was at the go-to statement that allows you to specify as transfer of control to one of many possible destinations in a program. The notion of so-called structured programming became almost synonymous with go-to elimination. Research had demonstrated that programs could be written without the go-to statement. The challenge of the era was for programmers to shift their styles to go to less programming, meaning less jumping around the code and a more sequential way of writing. So the results were impressive: more frequent on-time delivery of systems and more frequent within budget completion of software projects. Programs produced with structured techniques were cleaner, easier to debug and modify, and more likely to be bug-free in the first place. Research had demonstrated that all programs could be written in terms of only 3 control structures: sequence structure, selection structure, and the iteration structure. Just know that the one that we talk about the most here is iteration, or loops. So let's talk about the sequence structure. It's simple, unless directed otherwise. The computer executes C statements one after the other in the order in which they're written. This is the sequential or waterfall execution that we're talking about. And the flowchart segment illustrates the sequence structure. Now, we've already spoken in chapters 1 and 2 about the flowchart as a graphical representation of an algorithm or the portion of an algorithm, or it could be the entire program for that matter, or a business process. But understand the flowchart gives us an idea of the way that it works. Flowcharts are drawn using certain special purpose symbols such as rectangles, diamonds, and we call the arrows between each of these flow lines. Like pseudocode, flowcharts are useful for developing and representing algorithms, although pseudocode is preferred by most programmers. And the reason why is because programmers are not too fond of nice colors and shiny objects. They just want to know what's going to happen next. And 9 times out of 10, the pseudocode is very straight to the point. You need an X. Now you need a Y. Now we need to get this information. Now we need to get that information. We use the rectangle symbol, also called the action symbol, and we've talked about this in chapters 1 and 2. So we're going to keep on going. And here we go. Action. Add grade to total. Action. Add I to counter. Add 1 to counter, sorry. Now there's an easier way to write this. Counter equals counter plus 1 can also be written as counter plus plus. Counter plus plus is the shorthand to counter equals counter plus 1. You can also write the shorthand to this one being total plus equals grade. What that essentially means is total equals total plus grade, but that's a shorthand. When drawing a flowchart that represents a complete algorithm, a rounded rectangle symbol with the start and end, remember begin and end, start and end from the last chapter. Perhaps the most important flowcharting symbol is the diamond, which is your decision structure. It's your if statement. If this, then that. Otherwise, do X. And you have the small symbols called the connector symbols, and those are also very important. So, C provides three types of selection structures in the form of statements: the if else, and switch. Now, C is not the only program that has these. As a matter of fact, every language that I've ever touched has these three decision structures. An if statement performs an action if a condition is true or false, or a Boolean condition. Boolean condition is 0. Boolean literally means 0 or 1. It can only be one or the other, true or false. So when you hear me say Boolean condition, what I mean is the condition that must be satisfied in order that the if statement is run. So, if I am your professor, you owe me grades. So the Boolean expression is I am your professor, right? If I am your professor, or if I, Francis, equals your professor, then in that case, that actually is true. Therefore, you will owe me grades. Now, we can also have the second decision structure, which is an if-else. If I'm your professor, you owe me grades. Else, you're off the hook. The else is like a catch-all. It catches everything that is not in the if statement. Now, there's a fourth decision structure that I do not think we're going to speak about here. But there's the if-else if, which gives you the ability to have a second Boolean condition if you so desire. And it would sound something like this: if I'm your professor, you owe me grades. Else if Sally is your professor, you owe her grades. Else, you're off the hook. That's the way that pseudocode would run, and those Boolean expressions would be written. Now, what's the difference between an if statement, an if-else, and a switch? Well, if and if-else are pretty much just branches of each other. A switch is something completely different. What a switch statement is it literally looks at a variable to find out if that variable is true or false, based on a subset of case statements. So, switch, and let's say a variable is being filled saying, my name, Francis. And then down in the case statements, there's a case that says case string Francis. Now, if that is exactly what's inside the variable being determined to be by the switch, then yes, you'll have a true statement. Now, it's a little confusing, and I hope that they give you some code here so we can actually show you what I'm talking about. Okay, so here we go. We have our int main. Basically, that's where the program runs. Okay, if I wanted to write an if statement, this is how I would write it. I think it's just as easy as if, we'll say, it's not var, we'll say string. Could that work? str. I write a lot in C#, so writing in C, it's the syntax is different. Okay. If, I'll just do it this way. If 5 is less than 10, I want you to print out okay. So, and we're going to comment this out. All right. So in our main, we have an if statement. The if statement states that if 5 is less than 10, then I want you to print out that 5 is less than 10. So let's run this and see what happens. I don't really care. It's out of date. Okay. Here we go. 5 is now less than 10. So what happened? Well, 5 is less than 10. So this Boolean expression is true. Therefore, it's going to run whatever is in these little brackets here. Now, let's say, and I'm going to cancel that out. Let's do an else. Else printf, that's not true. And let's say that 5 is greater than 10. So we have our if, we have our else. If 5 is greater than 10, which is not true, by the way, so this is false, this will not run. Because this is not true, it'll go to the next part of the branch, the next part of the if-else branch, because that's what I wrote there. If I didn't write this else here, it would not execute anything, or it would just go and execute the rest of the stuff that would need to be executed and leave this if-else branch. But in this case, there was an else to catch everything that this could not catch in the if. This is not true, that's not true, you saw it there. Now, let's say I wanted to write else if 10 is greater than 5. What will happen? Well, this is going to be false. That'll be true. Therefore, whatever is true first, and this is why if-else statements are it's very important how you write them. Whichever one of these is true first is going to run, and the next one is not going to run. So, if 5 was greater than 10, this else if will never run. This will run whatever's in the middle here, and it'll skip and go to the next lines after the if-else branch. And you know where the if-else ends because of this closing bracket. Basically, what a switch statement needs is an expression. So it looks something like this. Switch. And then what I want to do is I want to have an expression based on something that's occurring or a variable that I have. So if I had a grading program and I had a character grade that equals B, okay, and I'm switching on the variable grade, okay. Then what I can do is I can write a subset of cases, okay. So case, let's just write it for all the grades, shall we? A, printf, case. I'll just write two cases. Case B, break. You can also write a default, and I guess I can do that just to show you what it looks like. The default does not require a break. What break does is it tells the case statement to no longer try to validate the cases. That's what a case statement does. It says, break here, leave the switch tree, go to the next lines. Now let's run this and see what happens. We should get above average. I'm banking on that. And true to form, above average. So, with that being said, that's how a switch statement works. Remember that an if-else statement and a switch statement are eerily similar, but they're not the same. Switch statements cannot execute Boolean expressions. They can only try to verify if a case is accurate or not. There are situations where you would use a switch statement. Switch statements are faster than if-else by a long shot, but they can't do branched statements. It's not that easy to calculate them. So, iteration statements: do, while, and for. C has 7 control statements, sequence 3 types of selection and 3 types of iteration. We talked about while and do, and we spoke about for in chapter 2, chapter 1. Control statements can be attached to one another. This is much like the way in which a child stacks building blocks. We'll learn that there's only one way control statements may be connected, a method called control statement nesting, which is a for loop within a for loop within a for loop. Recursive loops are the bane of everyone's existence. Try to keep loops at a bare minimum. If you find yourself having to use a loop, so be it. But try not to nest them and try not to use them overly. They can cause hardware failure and a lot of software issues. So, if a student's grade is greater than or equal to 60, print passed. This is a pseudocode statement for an if selection statement. And we've already gone over if, so I'm going to keep on going. If the condition is false, the printing is ignored. We spoke about that. The second line of the selection structure is indented, blah, blah, blah. We spoke about that as well. The preceding pseudocode if statement may be written in C as if, and we've spoke about that as well. We've actually went over this already. So we're going to keep on going. The flowchart of figure 3.2 illustrates the single selection if statement. This flowchart contains what is perhaps the most important flowcharting symbol, the diamond. The diamond is your if statement flowchart symbol. If the grade is greater than or equal to 60, print passed. Otherwise, do something else. That wasn't annotated here. The decision symbol has 2 flow lines emerging from it. One is yes and one is no. So keep on going. The if statement 2 is a single entry, single exit statement, meaning that there's only one way in and there's only one way out. The if else, we also spoke about this, is if the Boolean expression is satisfied, or if it's true, run the if and leave the if tree. If it is not satisfied, run the else and then leave the if tree. Indent both body statements of an if and else, both in your pseudocode in C to make it easier to read for yourself and for other people. If there are several levels of indentation, each level should be indented the same additional amount of space. Please, white space is so important. It makes things a lot easier to read, especially when you want me to debug your code. So, here's the if else. If the Boolean condition grade is greater than or equal to 60, is not satisfied. If it's false, then this if statement will be ignored, and it will go to the else statement. The else is a catch-all. Else is a catch-all. Whatever this doesn't catch, else will catch. If this was an else if, it only catches its Boolean expression. If its Boolean expression is also false, it will not run. So, if the grade is greater than or equal to 60, print passed. If it is not, print failed. So, conditional operators are also called ternary operators, and we use them in almost every language. The question mark and the colon stand for the, so you have your Boolean expression, grade is greater than or equal to 60, and then you'll have the question mark with the true statement, and then you'll have the colon after the true statement to annotate the false statement, like that. This is called a ternary operator. Grade is greater than or equal to 60. If that is true, pass is your string. Otherwise, failed is your string. This is an if-else statement written on one line. This is called a ternary operator. So, the second and third operands in a conditional expression can also be actions to be executed. For example, Nested if-else statements test for multiple cases, and in most situations, you can refactor or consolidate nested if statements by using the and the or operator. So, if the grade is greater than or equal to 90, print A, else if the grade is greater than 80, print B. We spoke about this, right? You don't have to do this, else. You can just say else if. These nested statements are not any faster or slower than an else if, but they're harder to read. If the variable grade is greater than or equal to 90, all four conditions will be true, but only the put statement after the first test will be executed. Now, here's the else if that I wrote in the code. If the grade is greater than or equal to 90, put A. Otherwise, if it's greater than or equal to 80, put B. Else if it's greater than or equal to 70, put C, so on and so forth. And then there's the else at the end. That's your catch-all. Anything that doesn't satisfy these Boolean expressions, the Boolean expression is in these parentheses here, grade equal to, and it's after the else if or the if. These are Boolean expressions. If there's no Boolean expression after it, that means everything else is an F, or whatever this condition is. And this talks about indentation and block statements, but we spoke about that as well. So, the following example includes a compound statement in the else part of the if-else. Compound statement is a statement that has more than one statement. So there's a statement that says failed, and then it says again, there's another statement after that saying, you must take this course again. In this case, if the grade is less than 60, the program executes both put statements in the body of the else and prints, failed. You must take this course again. So, we spoke about this as well in Chapter 2 and Chapter 1. A syntax error is a written error by the programmer that is caught by the compiler. You won't be able to compile the code if you have a syntax error, and the compiler will catch it and tell you about it. A logic error is an error that's affected when the program is run by either the user or tested by the developer. That doesn't necessarily throw an error. Sometimes the logic error is based on bad algorithmic array of events that we wrote incorrectly. A fatal logic error causes the program to fail and terminate prematurely. A non-fatal logic error, the ones that you really don't want, you want to try to avoid, allows the program to continue executing but to produce incorrect results. Just as a compound statement can be placed anywhere a single statement can be placed, it's also possible to have no statement at all. An empty statement is represented by replacing a semicolon where the statement would normally be. So, use expressions of the same type for the second and third operands of a conditional operator to avoid subtle errors. A compound statement can be placed anywhere in a program that a single statement can be placed. Always include your control statements, bodies, and braces. Always. 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 This is very important. Please, always use brackets. The way you saw me develop, there was not any conversation about these brackets not being there. They need to be there. These brackets denote to the program where the beginning of the switch statement is and where the end of it is. They denote where the beginning of the main is and where the end of the main is. These are very important. You cannot survive without them. You can write without them, but I'm telling you, your code is going to have a lot of syntax and logic errors. Please, braces. As in if leads to a logic error in single selection if statements, and a syntax error in double selection if statements. If statements don't need a semicolon at the end of them. Neither do switch. So, as you can see here, I did not put a semicolon at the end of this switch statement. This is the end of the switch statement. If I wanted to write this as one continuous line, I could, but there's no semicolon that's required here. The same for if. If else is if, else, and else if. Typing the beginning and ending braces of compound statements before typing the individual statements within the braces helps to avoid, as you saw, I typed the brace first and then I wrote my code inside. Okay. An iteration statement allows you to specify that an action is to be repeated while some condition remains true. While there are more items on my shopping list, purchase the next item and cross it off my list. The sentinel value is that there are no more items on my shopping list. The statement contained in a while iteration statement constitute the body of the while. The while statement body may be a single statement or a compound statement. Eventually, the condition will become false when the last item on the shopping list has been purchased and crossed off the list. At this point, the iteration terminates and the first pseudocode statement after the iteration structure is executed. Oh, don't spell any keywords uppercase. As you saw what I did here, this switch, all lowercase. My if-else were all lowercase. If you put a capital S here, it'll throw a complex syntax error. And you're going to send me emails asking me why. Whatever these keywords are, default, case, switch, if, else, else if, for, while, do, they're all lowercase. All of them. I know that might be counterintuitive, but there's a reason for that. C is case sensitive. Just like JavaScript is, just like PowerShell is. It's all case sensitive. So it's in your best interest to write everything in lowercase. It makes it easier to read too, but write it all in lowercase. It'll make your life a lot easier when you're trying to debug. You're sitting there going, why isn't it working? Well, it's probably not working because you used capital letters somewhere along the way, or you spelled it wrong or whatnot. So, as an example, and remember what I said, a while and a do loop, there's only one difference between the two. One of them asks for the Boolean expression at the beginning of the loop, and one of them asks for it at the end. The while loop asks for the Boolean expression before it runs the code in the loop. Once. The do doesn't ask for the Boolean expression before it runs the code. It runs the code one time, then it asks to see if the sentinel's been reached. So, in this case, product equals 3. So the variable product equals 3. While product is less than or equal to 100. Run the code that's in the while loop. What's in the while loop? Well, it's between these two curly braces here, which is product equals 3 times product. So if 3 is the number, 3 times 3 is 9. This loop's going to then go again. While product is less than or equal to 100, it's still less than or equal to 100, correct? Because it's 9. So run this again. 9 times 3 is 27. Product now equals 27. Run the while loop again. While product is less than or equal to 100, it's 27. Run it again. So 3 times 27 is a number. I think it's 81. So product equals 81. Run the loop again. While product is less than or equal to 100, do what's inside. Well, product's 81 is still less than 100. So what's 3 times 81? I think it's 243. So product equals 243. Is that right? I think so. So product equals 243. Run the while loop again. Iterate again. While product is less than or equal to, wait a minute, product is greater than 100. That means that this is false. Once this becomes false, or once the sentinel's been satisfied, in that case this has been satisfied, don't run this while loop anymore. So now that the product is 243, we don't have to run the while loop, go to the next line. While this is true, do this. And do that until the sentinel has been reached. It's been reached, 243, go into the false statement, or go to the next line, whatever that may be. When the while statement is entered, the value product is 3, and we went over this. Oh, look, they're the numbers. I did not read this beforehand, by the way. I did the math in my head. Don't try that. And it terminates at 243. To illustrate how algorithms are developed, we solved several variations of a class average problem. A class of 10 students took a quiz. The grades Integers in a range of 0 to 100 for this quiz are available to you. Determine the class average on the quiz. So how would we do that? Well, first we want to write pseudocode to kind of find out how. We don't know how many students are going to add that are, well, if I was the professor I would know, but in this case we don't. We also don't know what their grades are, so we need a way to get their grades. In this example, the iteration terminates when the counter exceeds 10, meaning that there's only 10 grades or students in the class. Counter-controlled iteration is often called definite iteration because the number of iterations is known before the loop begins executing. And that is not true majority of the time. Majority of the time, you don't know how many times you're going to have to iterate. The data can come back in all kinds of forms, and when you get it, it's all dependent upon what you're looking at. So, set the total to 0. This is the grades. Set the grade counter to 1. While grade counter is less than or equal to 10, input the next grade, add the grade into the total, add 1 to the grade counter. All right, when this is done iterating 10 times, set the class average to the total divided by 10. Then print the class average. And here we go. This is what it would look like written in C. You have your main, which is void. It's not returning anything. That's what that means. It's not returning a value. If you didn't have this void here, you would have to return a value. But the main's always void. It doesn't return anything to anybody. Unsigned integer counter, meaning that there's nothing assigned to the counter at this moment. Int grade, int total, int average. These are the 4 variables that we're going to initialize. We're then going to assign 0 to total. We're going to assign the number 1 to counter. While counter is less than or equal to 10, I want you to print the grade entered, or printf, I want this grade, scanf, read the grade from the user, and then I want you to add the grade to the total and then fill the total variable with the grade. And then I want you to increment the counter by 1. After all that's done, I want to take the variable average and I want you to assign the solution total divided by 10 to the average. Then I want you to print the average. In this case, the average is 81. So, the algorithm mentions a total and a counter. A total is a variable used to accumulate the sum of a series of values. A counter is a variable used to count, in this case, to count the number of grades entered. Because the counter variable is used to count from 1 to 10 in this program, all positive values, we declared the variable as an unsigned int, which can store only non-negative values. Unsigned means no negative values whatsoever. I don't know how you would get negative values in a test, but if you've done that before, please inform me. I've never seen that before. Variables used to store totals should normally be initialized to 0 before being used in a program. Null, 0, whatever the case may be. Counter variables are usually initialized to 0 or 1, 0. Everything in computer science starts at 0. Always. An uninitialized variable contains a garbage value. The value last stored in the memory location reserved for that variable, meaning you want to make sure that the value there is the value that you want. If a counter or total isn't initialized, the results of your program will probably be incorrect. And this is the example of a logic error. Always initialize counters and totals.